Hi, this video continues the discussion of how to convert an integer value into a floating point value. In the last video, I presented SystemVerilog code to convert integers into floating point values in cases where we don't need to round the results. If you haven't watched that video yet, you should do so before watching this video. A tag for that video should be appearing on your screen now. In this video, I'm going to extend the integer to float conversion code to deal with cases where rounding needs to be performed. I'm implementing the MIPS cvt.s.w instruction. As before, there are analogous instructions for ARM and Spark, so the work being presented in this video could be adapted for use with other architectures. As was mentioned in the previous video, this functionality is required by the IEEE 754 specification. Let's review the binary 32 format. It has one sign bit, an 8-bit exponent field, and a 23-bit significand field. We can quickly see that in the general case, a 32-bit signed integer isn't going to fit into a 24-bit significand field without some adjustments. The good news is that most or all of the code from the previous video shows up in this code, so our initial steps are the same. We test to see if the input integer is 0. If so, we return the binary 32 positive 0 value. Otherwise, we shift the input integer left to get a normalized significand. Then we use the number of bits we shifted the significand to compute the exponent value. Here's where we depart from the previous video. In the general case, we need to round our 32-bit significand so that after we've trimmed the implicit leading 1 bit, we can truncate the result to 23 bits in order to construct our final binary 32 result. The question now becomes, how do we round the significand? The IEEE 754 standard calls out 5 rounding modes: round ties to even, round toward 0, round toward positive, round toward negative, and finally, round ties to away. The final rounding type, round ties to away, is only required for the decimal floating point formats. Since I'm not implementing any of the decimal formats, I'm going to skip implementing this rounding mode. To implement rounding, we make the following changes. We need to be able to specify the rounding attribute, so this module has an additional argument named RA. In the general case, converting a 32-bit integer into a floating point value will lose precision, and the floating point value won't be identical to the integer value which was converted. We will notify the user of the loss of precision by setting the inexact flag. It's possible that when converting some integer formats to some floating point formats, that the integer is too large to be represented as a normal number, and we will have to return either positive or negative infinity. This necessitates the ability to return an overflow flag. With these additions, the argument list now looks like this. RA is a bit vector. Each bit in the vector represents a different rounding mode. Exactly one of these bits will be set to 1. It's an error if no bits are set, or if more than one bit is set. The include file, IEEE-754-flags.v, has been updated with new symbols for each of the rounding modes, plus an additional symbol, last RA, which is the number of bits in the RA bit vector. The inexact and overflow flags are single bits. We instantiate the rounding module with the following arguments. The inputs to this module are the most significant bit of W, which is the sign bit of the input integer being converted to a binary 32 value. EXPN is the value of the exponent we computed after we normalized the significand. In the previous video, this value was called EXP. SIGN is the normalized significand. In the previous video, this value was called SIG. The final input value is RA, which tells us which rounding mode to use. The module outputs EXP out, which is the exponent value after rounding, and sig out, which is the rounded significand value. Note that this value is only 24 bits wide. The corresponding sig in value is 32 bits wide. The rounding steps are as follows. Compute the rounding value round bit. If the value needs to be rounded to the next larger significand, this value will be 1. Otherwise, it will be 0, which will result in the significand being rounded down. Truncate the input significand value to nsig plus 1 bits and store in tsig. This corresponds to the value f, which I will define shortly. Add 0 to tsig and use round bit as the carry-in value. Note that the module padder24 was generated by the Python script padder.py. This script was described in a previous video. If you need a refresher, a link to the video describing padder.py should be appearing on your screen now. Calculate the rounded significand. If the carry-out value from the addition cout is 0, we use the output of the addition as our rounded significand. Otherwise, we shift the output of the addition operand one place to the right and prepend the carry-out value. Use this value as the rounded value rsig. Calculate the value of rexp by adding the carry-out value to the input value expin. Assign the values rexp and rsig to expout and sigout respectively. That's everything except the details of how we calculate round bit. To answer how we compute round bit, I'm going to start by examining the details of what it is we're doing when we round. Sig in is a 32-bit value. Its most significant bit is 1. To make this 32-bit value fit into the 23-bit significand field of a binary 32 value, we need to strip off the leading 1 bit and strip off the last 8 bits. This leaves us with a 23-bit value. Let's look at the sig in value in detail. This is a diagram of our bits. Again, the most significant bit is set to 1. The next 23 bits are some combination of zeros and ones. We don't know what their values are, so I have left those values unspecified by using x's. Likewise, we don't know what values are stored in the final 8 bits. Since the values stored in the final 8 bits are unspecified, I've used y's in place of the actual values. The IEEE standard says that the binary point is just to the right of the leading 1 bit. That means that the bits denoted by the x's and y's form the fractional part of our significand. The location of the binary point is marked by an arrow. For a moment, I'm asking you to imagine that the binary point is just to the right of the x's, placing it at the boundary of the x's and the y's. If we strip off the y bits, we're left with this. Since, for the moment, we're imagining that the binary point is to the right of the x's, the remaining number is an integer and has no fractional part. Restore the locations for the y bits, but fill the locations with zeros. The value stored here is still an integer because the fractional part of the number is 0. The significand, which has had all of its y bits replaced by zeros, is going to be called f. If we compare the value of f to the original value sig in, we can see that f is less than or equal to sig in. If the y bits of sig in are all set to 0, then f is equal to sig in. If any of the y bits are set to 1, then f is less than sig in. Now I want to add 1 to f. In this slide, the first set of 32 bits is our f value. The second set of 32 bits is how we represent the value 1 when the binary point is located at the boundary of the x's and y's. Note that the only bit set in the second set of 32 bits is just to the left of the binary point. It should be obvious that we now have the inequality f is less than or equal to sig in is less than f plus 1. When we shorten the significand from 32 bits to 24 bits, that is, when we're rounding, we're choosing between the values f and f plus 1. We use the value of round bit to make this choice. If round bit is 0, we choose F. If round bit is 1, we choose F plus 1. Stated another way, the rounded significand value is computed by the expression F plus round bit. How round bit is computed depends on the rounding attribute selected by the user. Since the default rounding mode is round ties to even, that's where I'm going to start. This is a diagram of the binary 32 value and its fields. Below that is the 32-bit normalized significand, which was passed into the rounding module. I've already discussed the three fields of the normalized significand, but I do want to add two definitions, which I will be using in the following discussion. I'm going to call the collection of bits with the letter Y, Y bar. This will be denoted by the letter Y with a line above it. Similarly, I'm going to call the set of bits filled with X's, X bar, again denoted by the letter X with a line over it. Since we're looking at the round ties to even rounding attribute, the binary value 1 followed by 7 zeros is used to divide the computation of round bit into three main cases. If Y bar is greater than the binary value 1 followed by 7 zeros, then round bit is 1. If Y bar is less than the binary value 1 followed by 7 zeros, then round bit is 0. If Y bar is equal to the binary value 1 followed by 7 zeros, then we have a tie, which leads to two subcases. If X bar is odd, then round bit is 1. Otherwise, if X bar is even, then round bit is 0. Why compare Y bar to the binary value 1 followed by 7 zeros? First, an explanation. To simplify the math, I'm pretending that the binary point is shifted n sig places to the right, so that the binary point is between X bar and Y bar. Doing this scales all of the numbers by a factor of 2 to the n sig power. This simplifies all the math. The math which follows isn't technically correct, but because I've scaled all the values by the same amount, it makes the explanation much simpler, so just go with me on this. Because the binary point is just to the left of the Y bits, Y bar is the fractional part of sig n. This means that the binary value 1 followed by 7 zeros can be written as 0.1 followed by 7 zeros. This value, in decimal, is 1/2. So we're asking, is Y bar greater than 1/2, less than 1/2, or equal to 1/2? When Y bar is greater than 1/2, that says the distance from sig n to F plus 1 is less than the distance from sig n to F. That is, sig n is closer to F plus 1 than it is to F, so we need to round sig n up to F plus 1. Likewise, if Y bar is less than 1/2, then sig n is closer to F than to F plus 1, so we round down to F. If Y bar equals 1/2, then the distance from sig n to F is equal to the distance from sig n to F plus 1. This is our tie case. To break the tie, we round sig n to the value F or F plus 1, depending on which of them is even. When X bar is odd, F plus 1 will be even. Otherwise, F will be even. Now that I've explained what it means to compare Y bar to the binary value 1 followed by 7 zeros, I need to explain how to actually compute whether Y bar is less than, greater than, or equal to the binary value 1 followed by 7 zeros. Since we're treating Y bar as the fractional part of sig n, we can write Y bar as 0 point followed by 8 Y's. If the most significant bit of Y bar is 0, then this fraction becomes 0.0 followed by 7 Y's. From here, we can see that 0.0 followed by 7 Y's is less than 0.1 followed by 7 zeros. So when the most significant bit of Y bar is 0, then Y bar is less than 1/2. Now consider the case when the most significant bit of Y bar is 1 and all of the remaining bits are 0. Then Y bar equals 0.1 followed by 7 zeros. That is, Y bar equals 1/2. How do we determine if all of the remaining bits of y bar are 0? We could individually test each of the remaining bits, but that solution doesn't scale well. If we OR all of the remaining bits of y bar together and the result is 0, we know that all of the remaining bits of y bar are also 0, so I only have to do one comparison. If we number the bits in y bar, making y7 the most significant bit of y bar and y0 the least significant bit of y bar, then the OR of the remaining bits is as follows. So when y7 is 1 and the OR of the remaining bits is 0, then y bar equals 1/2. Now it's easy to see when y bar is greater than 1/2. If any of the remaining bits in y bar is 1, then the OR of the remaining bits is also 1. When y7 and the OR of the remaining bits are both 1, then y bar is greater than 1/2. Now we need to reduce the computation of round bit to a logic equation. To simplify the equation, I define 3 Boolean values. Last kept bit is odd, deciding bit is 1, and remaining bits are non-zero. Last kept bit is odd is initialized to be the last bit of x bar. Deciding bit is 1 is initialized to be the most significant bit of y bar. Remaining bits are non-zero is defined as the OR of all the remaining bits of y bar. Using these 3 values, we can now compute round bit for the rounding attribute round ties to even. Hopefully you're satisfied that the logic equation correctly determines how we round for the round ties to even rounding attribute. For now, I'm skipping past the rounding mode round toward positive because the round toward negative attribute is just a little simpler. You'll see why when I talk about round toward positive. In section 4.3.2, the IEEE 754 specification says, the rounding direction attribute, round toward negative, is defined so that the result shall be the format's floating point number, possibly negative infinity, closest to and no greater than the infinitely precise result. Before looking at the logic for implementing round toward negative, I want to remind you that the first argument passed into the rounding module is the sign bit of our original integer input value. Inside the module, I refer to this bit as neg_in. If the original input value is negative, then neg_in will be true. To implement this part of computing round bit, I added the following clause to the logic equation. When implementing round toward negative, any positive value should be truncated. Without going through all the pedantic details, take a moment to satisfy yourself that truncating yields a rounded significand for positive numbers, which is always less than or equal to the unrounded significand. After all, truncating gives us the value f from before. Since we're truncating positive numbers, we need the expression to be false. At the top level, the expression is an AND expression with 3 inputs. If any of the input expressions is false, the whole expression is false and round bit will be 0. If our original input value is positive or 0, that is, if our original input value is not a negative number, neg_in will be false, so the whole expression will be false, so round bit will be 0, causing us to truncate significands for positive numbers. Now let's consider how this expression deals with negative numbers. The sub-expression, deciding bit is 1, ORed with remaining bits are non-zero, is false when y bar equals 0. When this sub-expression is false, round bit will be 0, so the significand will be truncated rather than rounded. We do this because, in this case, the truncated version of the significand is equal to the infinitely precise significand. It just has fewer bits of precision. If the sub-expression is true, that is, if y bar is not equal to 0, then round bit will be true, and we round down to the next binary 32 value. Take a moment to satisfy yourself that when we process negative numbers, that we will always end up with a rounded significand, which is greater than or equal to the unrounded significand. Also realize that making the significand of a negative number bigger makes the negative number smaller, that is, closer to negative infinity. The logic to implement round toward positive is the inverse of round toward negative. This clause only becomes active when not neg n is true, and not neg n will only be true when the original input integer is positive or 0. It's the 0 case which complicates the explanation of computing round toward positive. Now, if our original integer input value is 0, this part of the logic equation will still compute round bit to be 0. But even if for some reason round bit got set to 1 in this case, it wouldn't matter because at a higher level in the logic, we tested the input integer for 0. And if the input integer is 0, we construct the binary 32 positive 0 value and return that result directly, so the rounded significand from this module won't be used in our final result anyway. To confirm this, you can either go back earlier in this video or re-watch the preceding video. With that caveat out of the way, you should be able to convince yourself that this portion of the logic equation always returns a rounded significand value which is greater than or equal to the unrounded significand for positive numbers. And for negative numbers, the rounded significand will always be less than or equal to the unrounded significand. It's time to deal with our final supported rounding attribute, round toward 0. If you've looked at the code, you will see that when round bit is computed, that there's no clause which is active when RA round toward 0 is set. Still, I claim that in the case of round toward 0, the logic equation will do the correct thing. By definition, when RA round toward 0 is set, then RA round ties to even, RA round toward positive, and RA round toward negative will all be false. This in turn means that each of the sub-expressions which use these values will also be false. So when RA round toward 0 is true, round bit will always be 0. Since round bit will always be true for this case, we will always truncate the last 8 bits, leaving a 24-bit significand, which will never be farther away from 0 than the original 32-bit input significand. Again, if needed, take a moment to convince yourself of that. Now that I've covered the logic to round for each of the supported rounding attributes, let's go back up one level to see how to signal inexact and overflow results. Let's start with the inexact flag. After we've taken the absolute value of our integer input value and left shifted it to get the normalized significand, if all 8 of the least significant bits of the significand are 0 based on what we now know about how rounding is done, we should be able to see that after rounding, the number in the binary 32 output will be exact because the rounded significand value will be equal to the significand value we got if we truncate the last 8 bits. That is, our integer input value only needed 24 or fewer bits to be expressed exactly. So if any of the 8 least significant bits of our normalized significand is 1, then after rounding, we will have an inexact result. So we can compute the value of the inexact flag using this equation. This ORs together all of the bits in y bar. Computing the value of the overflow flag is just as easy. For the conversion of integers to floating point values, we will only get an overflow if the integer input is too big to be represented in our selected binary floating point format. When this happens, the floating point output value will either be positive or negative infinity. If the output is infinite, then the exponent field of the floating point number will have all of its bits set to 1, and we can compute the overflow flag using the following. For this code, please take note of the comments. When converting a 32-bit signed integer to a binary 32 value, why won't we ever have an overflow? Remember that the 32-bit signed integer with the largest magnitude is -2 to the 31st power. For the binary 32 format, the largest finite exponent value is Emax, and Emax for an 8-bit exponent field is 127. 2 to the 31st power is smaller than 2 to the 127th power, So for this pair of input-output formats, we will never have an overflow. Before wrapping up this video, I want to pose some study questions and suggest a possible exercise for the viewer. In the case that the carry out bit is 1, how do we know that the sum output by p_adder24 has a least significant bit of 0 and that by shifting the sum right, we aren't losing any precision? The second study question is to consider integer sizes 8, 16, 32, and 64 bits. And the floating point formats binary 16, binary 32, binary 64, and binary 128. There are 16 possible combinations for performing the integer to floating point conversion. Which of these 16 combinations can possibly cause an overflow? Is there a difference if we treat the integers as unsigned values versus signed? The exercise is to implement the round ties to away rounding attribute. You should be able to do this using the symbols I have already defined in the code. You can find the GitHub repo for this code in the description for this video. The next video will cover how I tested this circuit. Please share this video with friends and colleagues who might have an interest in this video series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.